Section 2.2, Separable Equations. So now as we begin Chapter 2, we launch into solving differential equations, and we begin with first-order equations. Chapter 2 is all about first-order equations, and then the beginning of Chapter 2 is about a certain subclass of first-order equations, the so-called separable equations. So remember, a first-order equation is one where the highest derivative that appears in the equation is a first derivative. So let's just look at an example. Let's consider the differential equation dy over dx equals x times y squared. And so what we want to do here is try to separate all the y's from all the x's in a multiplicative way. And what I mean by that is we'd like to try to get this x and this differential dx together, and we'd like to get this dy, this differential dy together with y squared. We try to get those together. So if you stare at this for just a moment, first, if we multiplied both sides by dx, the dx's would cancel here, and we'd have an x dx, but we would still have this y squared. So we also want to divide through by y squared, or multiply by y to the minus 2. They're the same thing. But if we do that, if we multiply both sides by dx and divide both sides by y squared, then we would get y to the minus 2 dy equals x dx. And notice we've successfully separated this equation where we've gotten the y variable and its differential separated completely from the x variable, all the x variables and its differential. So this is y only and this is x only. If you can do this, which you can't always do this, but if you can, then we say the original differential equation is a separable equation. And then we call this form the separated form of the differential equation. So a DE is separable if you can put it in separated form. Not all equations are separable, but you may remember that you studied these in Calculus 1 and then also in Calculus 2 because they're a very basic type of differential equation and they can be solved by integration. So here, the reason that this is such a nice form is because now we can just anti-differentiate this side and anti-differentiate this side. Notice here we're integrating with respect to y, and here we're integrating with respect to x, and these are indefinite integrals. So if we apply the power rule here, we get y to the minus 1 over minus 1. Here we get x squared over 2 plus c. And now notice that we could have picked up a constant of integration here, but I only wrote one constant of integration. The reason I did not write a constant of integration over here is because if I did put a plus c over here, and I put, say, a plus d over here, because these do not have to be the same constants, I could just consolidate them onto one side of the equation anyway. And it's going to be very important in our theory going forward that a first-order equation should only have one arbitrary constant in it. It's going to mess some things up if we have more than one arbitrary constant. So I'm not being sloppy here by not writing a constant of integration. I'm actually thinking ahead and saying that I know that I'm only going to have one constant. I'm just going to consolidate it onto the right-hand side of the equation. So if we do that, notice that what we have here is an implicit form of a family of solutions. It's implicit because y is not solved for. It still has a minus 1 power on it, and this is divided by minus 1. But they are solutions because they came from the differential equation and we just integrated. So this is an implicit form of the solution. But whenever possible, we want to put our family of solutions into explicit form. So we want to solve for the y whenever possible. And here it just takes a little bit of algebra to do. Why don't we multiply everything through by a minus 1? And now is y to the minus 1 is the same as 1 over y, so why don't we reciprocate both sides? Or raise both sides to the minus 1 power, however you like to look at it. But if we reciprocate this, we get this. If we reciprocate this, we get this. And now you could do a little algebraic cleanup here. The back of the book or my lab might do this. If we multiply the top and the bottom by, say, a negative 2 to get rid of the 2 that's here and the negative that's here, then up top we would have a minus 2. In the bottom, the negative 2 would cancel with this, and we would just get an x squared. If we multiply this by a negative 2, we get a positive 2c. So you could write it like that, or you could say, well, if c is an arbitrary constant, then 2 times c is a different constant, and we could rename that d. Notice that this, and this are all ways to say the same thing. They are all explicit forms for the one parameter family of solutions that constitutes the solution to this differential equation. So this is mathematically, there's no difference between this, and this. It's more cosmetics, that this is just another, these are other ways to say this, but we generally want things to be in an explicit form whenever possible. Just to give you a little heads up, MyLab will ask you to write your answers in implicit form for these problems. And I think that's just to make it easier for the computer to grade. But what you would want to do here is they'll give you instructions that say, write your answer in the form g of x, y equals a constant. So if you had something like this, they're basically telling you to throw all the x and the y stuff to one side and isolate the constant. So if we got this, we would just throw this to the other side, and you could write it like this. Or you could multiply through by a -1 and change the c to a d, and that would work. Or you could write this as a 1 over y and write it like this. All of these are mathematically correct, and all of these would be acceptable in MyLab. So pay attention to the form that they want your answer in so that you don't get frustrated with having a correct answer but one that's not in the form that MyLab requests. Okay, so we see that all there is to separable equations is if it's separable, we just separate it and integrate. So how could we spice this up? Let's take a look. Well, first off, we need to realize that not all equations are separable. If you take the very innocent looking equation dy over dx equals x plus y, and you say multiply both sides by dx, you would get dy equals x plus y times dx. And if you notice, if you distribute this differential dx, you get this. If you look at this, there's no way to separate and isolate all the x stuff from all the y stuff. And that's because you get this cross term here. And so it's just not possible. And what that says is that this equation is just not a separable differential equation. We can't solve it using the methods in that first example. We will have other methods in the next section for solving this, but we need to realize the limitations of our current methods, and not all equations are separable. Okay? So at the end of the day, you need to be able to write it in this multiplicative form where you have a function of y times the y differential and a function of x times the x differential. For some functions, h and g, you just need to be able to separate the y stuff from the x stuff. And in that case, it's separable. Okay, let's look at another example. So here we have dy over dx equals e to the x over the square root of y minus 1. Kind of a complicated looking differential equation, but really not that bad. You could think of it as if we cross multiply, or if we multiply this side by dx and multiply both sides by dx and multiply both sides by the square root of y minus 1, we end up with this separated form. And because it can be put in separated form, this is a separable differential equation. So once we have it in separated form, we're just going to anti-differentiate both sides. This side requires a little baby u substitution here, so I'll let u be y minus 1. Then the du would be dy. This would give me an integral that's the square root of u du. And we can anti-differentiate that, rewriting the u as the square root of u as u to the 1/2. We apply the power rule and get u to the 3/2 over 3/2. And we'll just sit tight for a moment and we'll finish this out. Here, if we anti-differentiate e to the x, we get an e to the x. We do need to pick up our constant of integration. Remember, it's a first order equation. We have to get one arbitrary constant in it. That's what our theory says. We don't want to pick up a constant on both sides because that would give us two constants. So we pick up one constant of integration and we leave this alone. And now to complete our u substitution, we need to trade the u in for a y minus 1. So I'll put this here. I'll rewrite this as a 2/3. I'll have a y minus 1 to the 3/2 power, and we'll leave this alone. So notice if we stopped right here, this is a one parameter family of solutions. This is an implicit form for the family of solutions. Okay? So MyLab may say, write this in the form of g of x, y equals a constant, and so that means you would just throw the e to the x to the other side, and this is what you would type in MyLab. So sometimes they're going to let you off the hook and let you just put in the implicit form. If they demanded an explicit form, we would just need to algebraically isolate for the y. So here I would multiply both sides by 2/3. And then I would raise both sides to the 2/3 power. Here it would cancel. And here I would get a 2/3 power. And then I would add 1 to both sides. And so the explicit form could look like this. And that's totally fine for me. You could also, sometimes the back of the book may take this Since c is an arbitrary constant and they multiply it by 3/2, they may just call this d, since you absorb that and get a new arbitrary constant. This would be fine for an explicit form of the solution. This would be fine for an explicit form of the solution. This would be fine for a implicit form of the solution, and so would this. Okay, so just pay attention to what the instructions are asking you for the form. Okay, so what about initial conditions? So suppose I'll just recycle this differential equation. We'll take the same differential equation. We already found the general solution, so we don't need to do that all over again. But what if I add an initial condition? Well, just like, and what are we asked to do? We're asked to solve this initial value problem. So remember from the end of the last section, what we did is we said, if you have an initial value problem, to solve the initial value problem, you first need to get your hands on the one parameter family of solutions. Now, just recycling our work from last time, this is the one parameter family of solutions. This is the implicit form. This is the one parameter family of solutions in explicit form. I'm going to show you that you can use either the implicit form or the explicit form, either one. And if you just proceed consistently, we can apply the initial condition, find the value of the constant in the family of solutions, and then get the solution to the initial value problem that we want. Let's do these one at a time. Let's work with the implicit form. And so I'm going to apply the initial condition to the implicit form to try to determine the value of c. So I just want, wherever I see an x, I want to put a 0. Wherever I see a y, I want to put a 2. And when I do that, here's our implicit form. I'm going to apply the initial condition where I put a 0 in for x, and I put a 2 in for y. And then I'll just simplify this. So this just becomes a 1 to the 3/2, which is 1. 1 times 2/3 is 2/3. E to the 0 is 1. And the plus c is a plus c. Notice this is an algebraic equation in the unknown c. We'll just quickly solve this and get c is -1/3. Now notice this is not the answer. What we're looking for is the solution to the initial value problem, and this is a very common mistake, so be sure that you pick up on this. This is not the answer to the question. The question is to solve the initial value problem, but the solution to the initial value problem is you go back to the general solution, you go back to this one parameter family of solutions, and you substitute in the value of c that you found. So all I'm doing is I'm going back to the family of solutions, and I'm letting c be the value that we found, and this is what I would box in as my final answer. Now this would be the implicit form, but if it doesn't make you put it in explicit form, this is perfectly fine. Okay? So on the other hand, we could have started with the explicit form of the one parameter family, and now we're going to apply the initial condition. So here's the one parameter family in the explicit form. If we apply the initial condition, wherever we see an x, we put a 0. Wherever we see a y, we put a 2. Notice this is an algebraic equation in the unknown d. So let's isolate and solve for d. So here, e to the 0 is just 1. 1 times 3/2 is 3/2. We get a 3/2 plus d. I need to get rid of this 2/3 power. So I'll hit this side with a 3/2 power, which will make the powers cancel. I'll hit this side with a 3/2 power. 1 to the 3/2 is 1. I'll throw the 3/2 to the other side, and I get d is -1/2. So then that means this isn't the answer to my problem. What I want to do is return to the one parameter family and substitute the value for d that I found. So I would just return to this, and where I saw a d, I would put in a -1/2. I'd box this in, and notice they don't look exactly the same, but they're algebraically equivalent. One is in implicit form, and one is in explicit form. So a key concept here is the concept, and I already let the phrase slip a little bit earlier, it's the concept of a general solution versus a particular solution. So up here, we would call this one parameter family. The whole family of solutions, we would call this the general solution. General because the c hasn't been nailed down yet. General because no initial condition has been applied to determine that c. This would be the general solution in implicit form. This would be the general solution in explicit form. When we dictate an initial condition, forcing us to find the value of c, and now instead of getting a one parameter family of solutions, notice this is one and only one function. The value of c has been nailed down. We call this a particular solution. This is a particular solution. This is in implicit form. This is in explicit form. So it's very helpful to understand the contrast between if you're talking implicit form, you have a general solution and a particular solution. You have a general solution and a particular solution when you're in explicit form. So in the homework, you're going to see a little bit of both of these, to where you're asked to solve sometimes to just find the general solution because you don't have an initial condition. Sometimes you're asked to put it in explicit form. Sometimes you're going to leave it in implicit form. But all of these examples should help you take care of those.